Welcome to this comprehensive tutorial series on neural networks. Over the next 3 hours, we'll delve deep into the fascinating world of artificial intelligence and its fundamental building blocks. Whether you're a beginner eager to understand the basics or someone looking to expand their knowledge, this series will equip you with the essential insights into neural network and their diverse applications. We'll start by demystifying neural networks, the backbone of modern AI. Next, we'll delve into the convolutional neural networks revolutionizing image recognition. Then, we'll explore recurrent neural networks mastering sequential data like text and speech. Finally, we'll unravel the BERT transformer model and embeddings, transforming natural language understanding. But before that, make sure that you're subscribing to this channel so that you do not miss out on any new updates on this channel.
This is Sai Vignan Malayala. So my overview for the session actually would be discussing on RNNs and CNNs, the advanced neural networks. But before going there, I just want to give an overview of what's a neural network. Okay. So before going to the advanced level, we need to have the basic understanding of machine learning, which I am expecting you all have. And secondly, I want you all to know what's a basic neural network also. Okay. So for just next few minutes, I'll discuss the basics of neural networks and then start with CNN and RNNs in this session. So what's a basic neural network? Okay. So let me take an example instead of giving a theory kind of scenario. So I think all of you have an idea of linear regression, the basic machine learning algorithm, right? So let me take an example of linear regression. Like there is some suppose an example. You want to predict the cost of a particular land based on the size of the land. Suppose I take an example like scenario like there's a land of 500 yards and the cost is 10 lakhs, and there's a land of 1000 yards, the cost should be 20 lakhs, and the similarity goes on. So if I take this example, what would you do? You obviously would try to get the best fit line, right? You would plot. Suppose I have five points. No, suppose 500 yards and 10 lakhs, 1000 yards and 20 lakhs, or 22 lakhs, or 19 lakhs. So what you would do? I suppose I have 5 points, the real time points. You would try to get a best fit line based on the y equal to mx plus no error value, and you would try to get a best fit line and make your model. So even if I ask tomorrow what would be the cost based on certain prediction of certain size, then you would say the line goes this way, so this might be the cost around. Okay, right? This is the basic scenario of linear regression with finding the cost of a particular land with the size of the land. Let me take the same thing, the one feature. What is the one feature here? We have only one feature, that size. We are trying to take the size and predict the cost. The feature we are using is size of the land, and the prediction output is cost of the land. So let me take the same scenario and apply it with neural networks. So I will take into consideration one single neuron. Because we have one single feature, I will take one single neuron. So in neural networks, I would say like we have y equal to mx plus c kind of curve. In neural networks, we have a better ones like ReLU. ReLU is an activation function and tries to get the best fit line for a particular scenario. Okay. So what neuron will do in neural networks? What neuron will do in this scenario? So neuron will take the input, apply activation function like ReLU, and generate output. Okay. So let me show the graph of ReLU first. Right. So ReLU is this. So the function of this is so what I said, the neuron, what it will do, neuron will take the input, apply what activation function, the ReLU, and then generate output. Okay. So ReLU, the function works is like max of 0 comma value. So if the land values, or if the value is less than 0, the prediction is 0. If the value is more than 0, the value itself. Okay, so in this case we have single neuron. The neural network will apply relu activation function and generate output. Okay, so it's clear. So just like you are predicting this way, in neural network predicts this way. That's almost similar, almost similar, because we have single neuron and we have linear network. I mean, basically linear inputs and linear outputs. Okay, right? So that is how we have converted a simple linear regression to a neural network model using ReLU. Okay, so this is with single neuron. Okay, because we have single feature. What is the feature? Size of the land, which gives the cost of the land. Now, obviously, in the real time scenario, we can't predict the cost of a land based on one single input. There are multiple other features, right? Like you might get the cost of the land based on different scenarios, like the popularity of the land, the area where it is present, the zip code, the neighborhood, what is the neighborhood of the land. So based on different scenarios the cost of the land differs, right? So in this scenario we can't use a single a neuron or a single feature. We have multiple features, so we need to use a multiple neuron based networks. That's how I'll go to little bit next level. That's a perceptron. Okay, what it's called? It's called perceptron. It is little complicated, but not much. Okay, so how do you define a neural network when you have multiple inputs? Okay, suppose there are three inputs. Suppose I say the size of the land and the popularity of the land, or the zip code, and the neighborhood of the land. What is the neighborhood? Are there any hospitals? Are there any schools nearby the land? Based on that also, I mean, the cost of the land differs. So we are trying to predict the cost. So we are giving three inputs and applying to a activation function and then giving the output. Activation function we are using ReLU in this case also. Okay, so this is how a multi-layer, I mean, neuron-based network, it's perceptron works. Okay, so the advantage in using neural networks compared to your linear regression model here is, see, when I take, suppose the the second feature, like the zip code or the popularity of the land, that also take into consideration, uh, like how much far is it from the nearest popular location, right? So that is what the perceptron or the neural network does. Based on your random inputs, it tries to take your features, and also if you apply a hidden layer, it will take multiple more features. So even without giving a feature, it can try to recognize more features and give you the output. Okay, so we passed suppose we passed three features here. So the neural network, it automatically identifies some hidden features from the input and generates the Y output. Okay, so you can have multiple hidden layers. So I have four inputs. So this is a hidden layer and the output. Okay, so based on my inputs, there are multiple features being recognized and giving me the output. So that is the intelligence coming into picture with a neural network. It is not just your features, it is trying to get more features and trying to get the best outcome based on your inputs. That is how simple neural network works. Input, hidden layer, and output. Okay, fine. Maybe a little more detail before going ahead. So, uh, I said what is an activation function already, right? So neural network actually has three layers. One is input layer, hidden layer, output layer. So input layer, what you could say is it is the starting point of the network. So values here used to predict are what in here. Okay, the input values basically. And secondly, we have hidden layer. So hidden layer I can call it's a magic layer. It's a magic layer. All the magic happens in the hidden layer only. Okay, so the activation amount of input values are calculated here. Okay, this can be one or more layers. It depends on the data set and the requirement. and thirdly output layer. So here the activation of uh, uh, I mean the activation of each of the find nodes is used to select the solution. So it's basically trying to approve a transaction or approve a result. So this is the you know output layer where activation function also has the intervention, and it is trying to approve whether a particular result is going out or not. Okay. So now, if I say what's a neural network, I think it's pretty clear for you. If there are more than one perceptrons present and joined in a layered fashion, okay, it's a layered fashion, we have a neural network. That's all. So, what's a perceptron? A single neural network layer, single neuron layer. So, if you have multiple perceptrons, that's when you get a neural network and it has multiple layers. So, it's a layered network. Okay. So, here what happens? The output from the first layer goes to the input of the second layer, and goes on to the activation function, and the activation function finds the confidence level and makes the final decision for the output. That's simple. A neural network. I think with this definition, anyone who wants to understand what is neural network becomes clear. Okay, so simple, right? Great. Okay, let us move a little forward. Okay, so what are how do this neural networks learn? How do they learn basically? uh, we are giving inputs, we have hidden layers to identify features, there is activation function to approve no the threshold and give the output. But still, where is the learning happening? So there are two ways how the learnings happen in a neural network. So one I can say is feed forward way, and second is back propagation way. Okay, so how do they learn? There are two ways: feed forward way and back propagation way. Okay, so in feed forward way, the data travels from one direction. That's all. Input to output. Okay. Uh, so basically, in feed forward way, the results are very faster when you apply the model in real time, but the training is very slow. And most of the vision and speech recognition API, most of the vision and speech recognition based applications are run in feed forward way only. Okay, so it is what simple one direction way, that's all. And what is back propagation? It's like whenever you give input, it goes feed forward from one direction and goes back to relearn. That's how it learns. Okay, suppose I'll give an example. Uh, you have you have an no example. You already have an example, the land example, right? So based on the size of the land, you are trying to predict the cost of the land. So I gave multiple inputs, and then the the model has tried to predict that based on this value, 500 yards, the cost of the land could be maybe 8 lakhs, but the actual present value in the market is 10 lakhs. So the model has understood I gave a wrong input, there's an error of 8 minus 10, that is 2 lakhs. So it will go back propagate as an input to the first layer and say no, there's an error. So it's trying to relearn, it's not 8, it is 10, and then goes forward. And again, if it is trying to again retrain and again say it is 11 lakh, no, again it will go back and say It's 11 but actually it's 10. 10 minus 11 is minus 1, so again there's an error gap, so I'll relearn again. So that is how neural network does back propagation and relearning to get the right accurate result. Okay, so mostly the back propagation way works well, obviously because of the relearning happening there. So back propagation, so what it is trying to do, it is trying to minimize the cost. So what is cost? I think it's a new word, so let us note these are the real time words we have to learn. Okay, so what's the cost? Cost is just the difference between the actual, or I can say the actual value, sorry, the predicted value of the model and expected value from data set which is predefined in the market. Okay, so yeah, so that is cost. So when I say back propagation, you have to still remember the cost. So cost is what defines the back propagation. So the minimum the cost, the more accurate your model. The larger the cost, that means the greater error. Okay, so the goal of any neural network model is to minimize the cost. Okay, so what is the goal of neural network models? Or any machine learning models, I can say, minimize the cost, basically the error gap. Okay, how do we do it? How do we do it? Yeah, so basically uh, what happens in real time is this can be achieved by altering the weights and biases in the name of neural network game. It's a game. Okay, so by altering weights and biases, and the common method to do is gradient descent. A new word. I think you have learned a lot of words. Feed forward, back propagation, cost, and how to minimize the cost, gradient descent. So what we do to achieve this, the solution is alter weights and biases, right? Popular method is, sorry, gradient descent. I'll explain what is this. So what is gradient descent? Okay, so getting minimum cost by summing up the difference between actual and expected output multiplied by the learning rate is called gradient descent. Little complex, right? I'll give like kind of formulation for it. So it's basically the sum of the difference of what we already did that, right, of different outputs into learning rate, right? And the most common method of doing this is doing the gradient descent is using mean squared error. I think most of you have heard, who knows machine learning, what is mean squared error. So based on mean squared error, you're trying to predict the global minimum, or using gradient descent, you're trying to predict the global minimum. Again, a new word. Another new word is learning rate. Okay, so when you're trying to predict, you have obviously the errors, and to minimize the errors, I mean, in the by doing back propagation, you're you have a popular method, gradient descent, where you're summing up all the values, no, predict minus expected, predict minus expected for all the different nodes, and then multiplying by the learning rate, and then trying to find the global minimum. Wherever is the global minimum, based on those, you will get the minimized cost, which is the goal of a neural network. Let me explain that. So there's a formula for a mean squared error. So obviously you might have all known the sum of these things minus the mean and the value, mean and the value, mean and the value. So this is called gradient descent. And now, how to minimize the cost? Right. The actual minus predicted into learning rate. Actual minus predicted into learning rate. Actual minus predicted into learning rate. Right. So this is how you learn. This is a formulation. If I just go to the value, you can. It's pretty simple. Alpha is the learning rate. Okay. So alpha, the learning rate, a way to find the global minimum. How so how low is the step or how big is the step? Based on that, you will define the error rate. Suppose it's like a valley. Before going ahead to the gradient descent, I can say it's like a valley. Okay, right. There's a valley. So suppose you want to get the minimum global minimum. This is a global minimum, right, in this curve. So you initially start here. So if you take a larger step, what happens? You go here. Again you roll down to here. So there is a large error gap. Again large error gap, large error gap. So you the most of the time in training goes just to roll down, roll down, roll down. If you're here, you're rolling down. You're here, rolling down. You're here, rolling down. So to get the global minimum, you're suffocating. You're taking a larger learning rate and stepping ahead. Bigger step, bigger step, bigger step. But it is not a global minimum, so roll down. Again a bigger step, roll down. Again a bigger step, roll down. Right? So you take a larger learning rate, then what happens? You might train it faster, but still the accuracy is very low. You're not trying to get the global minimum. Or if you say no, I'll not take a large step, I'll take a smaller step, I'll do less learning rate, maybe 0.001 learning rate, very small, very slowly I'll learn. Yeah, you can learn it slowly, slowly, slowly. You can reach the global minimum. But the problem is this will take lot of time, lot of time. Where are you? You might be here, you might be here, anywhere, right? And if you take a smallest learning rate, then it will take longest time to reach the global minimum. If you take the largest step, then the time might go in just rolling down, right? So that intelligence comes to you when you're training your model. You have to choose the learning rate as a hyperparameter and take the right learning rate. Say that it is not too slow and it is not getting too error, too much gap. That intelligence comes to you just right. Okay, so this is what the learning rate does and tries to get the global minimum. And if the global minimum is correct, then your error rate is less, and then you have the right less cost value, and then your network is working very well. Okay, this is another photo example, right? So this is how the neural network learns. Okay, so there are two ways to summarize: the feed forward way and the back propagation way. So the back propagation way, it goes to relearn the model. The goal is to achieve the smallest cost. That is, what is cost? The difference between the actual the predicted value and the expected value is called cost. The minimum the cost, the better the model. And this can be achieved by using gradient descent. Gradient descent tries to minimize the cost by multiplying the learning rate and also decreasing cost and finding the global minimum. Okay, I give you the formula too. So this is how a neural network learns based on these inputs, slowly, based on your hyperparameter tuning. So be careful when you train later. Huh? Right. So we have covered two things: basic understanding of neural networks and how do they work. And we have learned a lot of different wordings in the real time: the cost function, the minimum, the learning rate, the gradient descent, and all. Okay, so going ahead, so what is advantage of using neural networks? Pretty simple. If you are using a large data set, if you have a large data, it doesn't work with your traditional machine learning algorithms at all, like SVM or linear regression or logistic regression. This won't work with your large data set. They don't have the capacity to work with such large data set. So that is a limitation of machine learning basic models, traditional models. And deep learning works very pretty well with a large data set to learn and train themselves. And more the data, the better the performance of the deep learning algorithms. That's an advantage. Okay, because it tries to capture the more features and better understanding. So that is the first advantage. I'll just write it down before going missing it. So it works pretty well with large data, which is not possible by machine learning traditional models. Okay, and what is the second advantage? The deep learning models have an advantage in considering n number of features automatically. Okay, it can auto detect n number of features. Okay, it can auto detect n number of features even without you mentioning it. You give an image to your neural network model, it can go through hidden layers and number of nodes and all. It can try to find faces even without mentioning which is ear, which is mouth, which is eyes, which is hair. Just give the data to as an image, It can find the features, which is head, which is face, and which is ears automatically, which is the color, which is the background, everything so detailedly. That is an effect of using neural network model. It can auto find the features. Okay. Thirdly, it is highly capable and scalable with good computation. Basically, basically you can choose a computation with deep learning algorithms. You can choose how much learning rate. No, you can choose n number of hyperparameters. We will discuss in the future too, with the code. Okay. Based on the activation function, also you can choose which is the right activation function for the learning rate, for the computation time and all. You can trigger the learning rate based on the gradient of different activation functions. Different functions can update different parameters at different learning rates. Okay, that's an advantage. If you use a sigmoid function, then the learning rate is little different. If you use a uh, relu, the learning rate is different, and based on the activation functions, you can trigger the gradient descent also. Okay, so these are the some of the advantages I can say. You can trigger every hyperparameter. That's a major advantage in deep learning. And what are the use cases? If I say, I think you already might have heard from the market how deep learning is used currently. So you have lot to say. Translation of text, identify faces, recognize speech, read handwritten text, control robots, what not you are able to do with neural networks and deep learning. Great to see this. Before going ahead, I would say we need to have proper understanding of different activation functions which are used in neural networks. So let me give a brief of activation functions. Firstly, I would start with sigmoid function. So obviously, the you might have already heard of sigmoid. The value is one plus one per, one pl- one by one plus e power minus c. So it's like the curve, the sigmoid curve, as I'm showing in the screen. So basically, this function is used more primarily for predicting probability in your in your code. I mean in your data set. And secondly, threshold function. So threshold function, obviously one or zero, like a step function only. Okay. So this is used. Uh, I mean, when you don't want any uncertainty in the middle, of your learning. I mean, in the middle of your data. Okay. So if you don't want any worry on uncertainty of in the middle, then you can go for threshold functions. Thirdly, obviously, ReLU, the most popularly used one. So it is a value if it is greater than zero input. It is negative. It is zero if you give negative value. So it basically works only for positive values. I mean, it only accepts or approves only positive values. Okay, it's most used ReLU. ReLU is rectified linear unit. And lastly, the other popular one is tangent, hyperbolic tangent function. So it's almost similar to sigmoid function, except that sigmoid is from 0 to 1, tangent function is from -1 to 1. Okay, that's why there is sigmoid I just mentioned, 0 to 1, -1 to 1. Yeah. So that with this we have covered two more things: the advantages and uses of neural networks in the real time, and activation functions. What are the different activation functions? And lastly, I would mention you the different types of neural networks. Okay, so I mean different types in sense currently there are many types of neural networks being used in the market, but one of the popular ones are, one is obviously standard artificial neural network. Second is RNN, and third is CNN. So I'll be discussing with code on artificial neural network, recurrent neural network, RNN and CNN in the next sessions. Okay, so these are very important if you want to become a good deep learning master. These, at least these three algorithms are necessary in neural networks. Okay, so ANN, RNN, and CNN. I'll most probably cover ANN to a little and RNN and CNN to a little detail. Before that, uh, small information on these three types of neural networks is like kind of ANNs, or the simple standard no networks. They are generally feed forward. Okay, and mostly used in vision and speech recognition type of scenarios. and RNN. These are called recurrent neural networks, and the word says recurrent, that has a significance. So here the neural network saves output to be used for future prediction. So every output is an input again. Okay, every output is a past of new input. And some of the popular use cases in RNN is text to speech, and thirdly CNN. So this ANN, input, hidden layer, and output layer. This RNN. So every output is an input. See, A got an output. This is again an input. Okay, and if you go in detail with multiple neurons, this is the case. No, input output, like it will rotate. Okay, like it is learning every time. JAZZ. So it is learning from the new inputs. Okay, so that's how RNN works. And so there's also a complex RNN. And lastly, CNN. So the advantage of CNN, also very popular neural network, CNN. So here the input features are taken in batches as if it's a filter, like shown in the figure. Okay, so basically this is the you're not training completely. You're training in batches. You're training in batches like a filters. Okay, that's why when you train an image in CNN, even if you again even if you want to predict some smaller value of an image also, it will work. Suppose you gave you in your image you have a face, you have a building, you have a traffic signal, everything. So even if you try to predict a traffic signal, it will try to get, because it is taking into batches and training faster, and also taking n number of features here. And there are a lot of other layers, I'll explain in later. But the main functionality compared to other networks is it trains in batches, and it takes multiple input features again there. So this helps the network to remember an input like an image in parts. And the examples is obviously image processing, facial recognition, kind of scenarios. Great. So with this, we have covered the overview of what is a neural network, how do they work, what are its advantages and uses, what are activation functions, and what are different types of neural networks, which will be going forward in detail. Thanks, guys. It was nice to take this opportunity. Thank you. Okay. Let's proceed now. So now I'll be explaining an example with a use case. So let me take a use case. I have a data set, okay, so which is a data set of diabetic patients. So this is a data set, the Indian diabetes data set. So it has 9 columns, so 8 features and one outcome, 1 and 0. One is having diabetes, 0 is not having diabetes. So there are 7 features based on which I am detecting whether a person has diabetes or not, without even going through a penetration test or something. Without extracting blood or something, just by having these records, I can predict whether a person can have diabetes or not. Okay, so I have 8 features and one outcome. Okay, and this is downloaded dataset from National Institute of Diabetes and Digestive and Kidney Diseases. So you can get the source here. And the number of instances is 768 examples, and number of attributes is 8 classes. So what is the first attribute? Number of times being pregnant, plasma glucose concentration, diastolic blood pressure, tricep skin fold thickness, 2 hour serum insulin, sorry, body mass index, diabetes degree, function, age, and lastly outcome 0 or 1. So what is 1? Tested positive, has diabetes, otherwise 0, no diabetes. So it says 0 or 500 instances, 1 is 268 instances. Just check the standard mean and standard deviation also here. So these are the records. So this is the first one is what, number of times being pregnant, and a last is age. Okay, so 6 times being pregnant and the age is 50 years. Okay. So there is a lot of data, 768 records. So there is a person with 5 times being pregnant and the age was 38, 55, 35, 28. My god, it's a low age. So I think there's a good data here. Let's go and implement our model with this dataset. I have already downloaded this dataset. I have it here. I'll just copy this path and let me go there. The use case is what? Predicting diabetes existence. Okay, fine. So that is my use case. So I will be using Python Keras. So the prerequisites for this library of Python Keras is you should have TensorFlow installed, and you should have Cbon installed to make our to make our view if required, to make our visualization if required, and you should have SciPy and NumPy installed, and TensorFlow and Keras installed, obviously. And the steps I will be following are below. Okay, so how will I go through my lecture is by this. So firstly, I would loading my dataset. Secondly, I will define my Keras model. Thirdly, compile it, and fourthly, fit my model to x and y, and then fifthly, evaluate it, and sixth is make prediction. Okay, these are steps I'll be following. So there are 768 records, as you see. So let me get the dataset. The file name is this. I just copied it, right? This is the file name, Indian diabetes data. Okay, let me load it here now. How do I load it? So I need to import no, load text, maybe, because I can load with load text from NumPy. Import load txt. Okay, now I say load dataset equal to load txt of file name, and because it's a CSV file, if you see, it's a CSV file, comma delimiter equal to comma, it's comma based, right? And I print my dataset. Sorry, okay, from NumPy import dataset, import load text. So I got an array of 768 records and 9 columns. Okay, so first 8 are my features and last 9 is my prediction. That I think we're clear, right? Okay, so now I need to define my train and test, right? So what is my training? So it's the first 8 features, right? So I'll take X as my input, which I'm giving to my neural network, artificial neural network. Okay, so it's my data set of all the rows and 0 to 8 columns except the last one. Okay, and lastly Y dataset which is my predicted or actual value, all the rows comma 8th column, right? So I will have my X and Y defined input and the actual result defined. So now I'll be using sequential model. So in Keras there are multiple ways of doing models, but the most preferred way for ANN, RNN, CNN is the sequential model. So sequential model as it is like feed forward model. uh, I'll define that. How do I define it? From Keras dot models import sequential. Okay, I need to also get my dense layer, because you need to have layers in your model at a neural network. So you have input layer, you have hidden layer, you have output layer, as we have already spoken. So all these layers are dense layers or the feed forward layers. So we need to have a layer, dense layers, used in Keras also. So from Keras dot layers import dense or dense layer. So there can be multiple type of layers based on the use case. So it can be convolutional layer or any other layer, whatever. So currently we are using dense layer for our basic ANN model. Okay, perfect. Now let me define. So what we have done, we have loaded dataset. We have defined Keras. We need to define Keras model now. Okay, so model equal to sequential. So it's my sequential model. Now I will start adding dense layers. So model dot add dense, and the dense layer input layer should have 12. 12 nodes, suppose, and input dimensions equal to 8. And for every layer we have an activation function to go to the next layer. So activation is, what is it? By default we have spoken ReLU, rectified linear unit, because it's an input layer. We have activation as ReLU. Input dimension is 8, so the output comes as 8. 8 features. Sorry, the input comes as 8 features, and this is my input layer. Now let me go to my hidden layer. This is the second layer, dense, and it has 8 outcomes, obviously 8, and I'll be giving 8 inputs to this. And the activation is obviously what? ReLU, because it has to go to next layer, the output layer, sigmoid functions or something. So now I have third layer, model dot add. I will add again the dense layer, and now, as we have already known, we have only one outcome, 0 or 1. 0 means no diabetes, 1 means has diabetes. So my input layer is defined, hidden layer is defined, and lastly my output layer after the activation should be single value. So I should have only one return result, one node basically. And the activation is what? Sigmoid. What is sigmoid? 0 or 1, right? You only get 0 or 1. You don't get anything else. ReLU you get 0 or the value. Value can be 1, 2, 3, anything in ReLU. But sigmoid you just get 0 or 1. So you're activating whether it's 0 or 1 and trying to predict the model. Basically this is the outcome or the outcome node. If I take the example, see, input layer, the hidden layer. So here we have multiple hidden layers, but in the code we just implemented one hidden layer and one output sigmoid function layer. So here we'll have activation sigmoid function. Here we may have ReLU. Here we have input and the ReLU activation, hidden layer, ReLU activation function, and then sigmoid function, and then outcome. Okay, that's what I'm doing. I have 3 layers, and the outcome is binary classification. We want to predict 0 or 1. So sigmoid layer is the best for it. Right. Let me do run it. Yeah, it's fine now. So model dot I want to compile my model now. So model dot compile, and the loss is what? I have binary classification being going on, right? 0 or 1. So I will use binary cross entropy for the loss. And then obviously we need to have an optimizer. I will explain what is an optimizer in detail in next sessions. So optimizer, I have an optimizer equal to, by default it is Adam. And lastly metrics, the metrics in which I want to train my model, focusing on. So I want to focus on accuracy, so I am giving the metrics as accuracy for my model. Okay, let me run it. Perfect, it has compiled now. So my model is actually compiled with dense layer and all these high-wire parameters. Now let me fit my model with the data. So model dot fit. Now my data comes into picture, x comma y, and what else? How do I fit the model? I need to also run on multiple iterations the epochs. So let me take epochs as 150. So it is like continuously learning with all the propagations going on. So it's learning with epochs again and again. So model outfit x comma y, input and output, to learn output, and x is the input. Epochs is 150 iterations, and then I want to train it in batches to avoid the computation issues. Batch size is 10, suppose. So batch underscore size is 10. So model dot fit. Right. The issue is the spelling epochs. Now it's training 150 iterations. If you see, my accuracy is increasing. See, and loss is decreasing. That's how it will help to fit the model with best epochs and batch sizes. So I have 768 records. Epoch 1, epoch 2, epoch 3, and loss is decreasing, the accuracy is increasing. If it's not going that way, then there's an issue with the model. So we have 150 iterations and all the iterations are done now. Okay, perfect. So let me check now the accuracy. Model dot evaluate. I want to evaluate my x with y. Okay, and let me print the accuracy, and it's into 100, right? So I have 75.1% accuracy. It's almost 75% accurate model I got with my training dataset. Okay, let me predict now. Just check me. Let us learn how to predict it with the sample values. So model dot predict classes. I want to predict 0 or 1. Predict classes x. So I just give the x values. I don't have any test data set currently, right? So I just will give the train data only, and let me check the predictions. And let me see just top 5 predictions after that. So for I in range of maybe 5, print x of I dot maybe to list comma predictions. Okay, I think we should not confuse it, so let me do predictions, and then predictions of I, first one, comma the actual output. Okay, so here this is the input, this is my prediction, and this is my output. Okay, let me write it here. Okay, let me print it first. Prediction spelling is wrong, sorry, the comma is missing, sorry. See, this is my input, the predicted is 1, actual is 1, 0 0 1 1 0 0 1 1. So it has trained perfectly. I have predicted it properly till now, and it was 75% accurate anyways with the x itself. So this is how you can actually train a simple diabetic model also with the particular instances, and train your neural network with just one hidden layer. Okay, I think this is the base for it. Okay, just go through it and you can do wonders with it.
And deep learning by IIIT Bangalore at upGrad and gain the skills employers are looking for. With a practical industry-aligned curriculum and hands-on project, you'll not only learn from the seasoned experts but also apply your knowledge to real-world scenarios. Don't miss out. Click the link in the description to start your machine learning journey today.
So, in the last session, we have discussed the basics of neural networks. What are they? How do they work? And what are their use cases and applications? And also, I have given a sample use case of detecting whether a person has diabetes or not based on some 8 features, and we have applied the ANN model to it, right? So, my main thought of explaining this is I have seen many students who are not so clear with understanding neural networks, the base. So I was keen in explaining all these concepts. What's a neuron? What's the difference between a linear regression and prediction with a neuron? And then what's perceptron? And what is neural network? And what is artificial neural network? And what are its use cases? So you can go through that video. You'll get a good understanding how the machine learning has evolved through deep learning through a neuron and perceptron and neural networks completely. Okay, and hope it helps you. Here in this session, I'll be explaining what is CNN. So CNN is a special case of neural networks. The type of neural networks, it's called convolutional neural network. Okay, it's very popular nowadays and has lot of use case. Okay, so the best image for this is this one. So the flow of convolutional layer or a convolutional neural network goes this way. So it has an input layer, the convolution layer, and the max pooling layer or the pooling layer, and again the convolution layer and then pooling layer, and how many ever you want, the same flow, and finally the activation function for the sigmoid and the predictions. Okay, so that's what happens. So it has basically two main things which you have to know. One is convolution layer and pooling layer. Okay, so what is convolution layer and what is pooling layer? As you already know, the advantage of CNN in the real time is even if you don't give any features as input to CNN, it can detect the features automatically internally. Okay, that's what is the advantage of using CNN. You give an image, it can internally find out different features, the eyes, nose, or the objects. How is that possible? So the advantage of CNN is it doesn't take the whole input or the whole image as complete and process it. It takes the input as patches. Like you see this yellow color, it's a small patch. That's what happens. It applies the convolution to the patches. So the word convolution means uh, in the real time it's called, it's like math combination of two functions to get a third function. Okay, that's what is convolution. So what here it is doing is the same thing. Here the convolution layer is done on the input data with the filter or kernel to get a feature map. That's what is happening here. So it is taking one image and then doing the convolution to get a feature map. And the pooling layer, so uh, it's again trying to rescale the feature maps which is it has got. Okay, so basically the size of the data is very big when you go to convolution, right? And it takes a lot of time to compute or to process it. So that's when we use the pooling layer which can downsample the feature maps and summarize them accordingly and get the features. So what is a convolution layer? If I ask now, it summarizes the presence of features in the input image. How does it do that? It does by the combination of input data with filters to get feature maps. And what is pooling layer? Pooling layer is just doing downsampling. So it is progressively reducing the spatial size of representation to reduce the amount of parameters and computation in the network. So the best method of pooling is max pooling. There are many average pooling, max pooling, mean pooling. So max pooling is one of the popular thing. So it is just taking from a feature RAM or from the kernel the max value and then doing the pooling or multiplying. So that's how you can have multiple convolution layers, one, two, three. Okay, so each layer has two things: convolution and max pooling. So do remember that we will be implementing the CNN using this format only. So here we will be using Keras. Okay, Keras as the library. Hope I think you are clear how CNN works, how it is able to auto detect the features, how it is using convolution, how it is finding feature maps, how it is doing pooling, and finally the layers, complete layers, and the output. Right? That's how CNN works. Okay, I'll go through this detail in further too, and I'll be explaining this code this CNN through an example of code with a use case. So the use case I have is obviously nowadays if you see there's COVID going on everywhere. So I have taken COVID as an example or a use case. So I have a good data set of different X-rays of humans. I mean human lungs who has COVID and who doesn't have COVID. Okay. So based on just giving this X-ray as an input to my model, to the CNN model, I can detect whether a person has COVID or not. Let me show through all this thing. So I have a good data set. So these are the lungs X-ray of different people who have COVID. So this I am giving as an input to my model, and I have normal people who don't have COVID, even their X-rays. I am also giving this data as an input to my model, and with this input, I am trying to predict if a new image comes. I should be able to say, my model should be able to say whether a person has COVID or not. So wonderful use case, right? Also very useful in the real term. My use case is predicting if a person has COVID or not by analyzing lung X-rays. I mean, not analyzing, basically by using lung X-rays as input to CNN or convolutional neural network. I hope the concept of CNN is clear. I'll go through it detail with every parameter explanation, with every layer explanation further. For the image to see, please go through this image for a few seconds. Right. So now I have my use case ready. I have my data ready. If I show my data, this is my data, train data, validation data, and finally I want to test it also with special data. That's what is this. I have my data. Fine. Let's start with the prediction of COVID using CNN images. Firstly, what I need to do, I need to import my data. So I need to import my libraries before that. So import NumPy, the basic one, and I want to also import matplotlib to visualize later, and import Keras, the library which I'm using for CNN, no, I mean CNN modeling, and I want to get my dense layers and convolution layers, right? So Keras has this called keras.layers. Yeah, keras.layers. Import. There are multiple layers I want to use: max pooling, dense, sequential. I mean, dense, max pooling, dropout, everything. So I'll import all. So from again, I want to import my CNN model. I have multiple models, sequential model also. So keras.models import sequential. Let me import all, otherwise I may use it. And I am processing my images, so I have to get the image function for it. So keras.processing import image. So these are my libraries which are required as of now. Perfect. It has been imported. So going further, I am taking a sequential model, obviously, which I have explained in the previous session also. What is sequential model? And let me do model.add my first layer, the input layer with convolution. So convolution of 2D, because it's an image, I will use 2D convolution, and the filters, the filters or the kernel is 32 I'm using because it's a big image. My image size to mention, I forgot, is 244 by 224 by 224. The image format I'm using is 224 by 224. So for that I'm using the filter or the kernel size as 32. Okay, sorry, the filters as 32. Okay, I'm using 32 as filters, and my kernel size I can take 3 by 3 kernel size, which is pretty simple for computations, and pretty obvious for the size I'm using. And the activation function is obviously relu. I have explained what is relu, the rectifier linear unit. In between in any layers or any model, you have to use relu to continue for the next layers, obviously, because the relu has 0 or the value option, not any other function has it. And the input shape already known, 224 by 224 by 3, obviously 3, right? So my convolution layer 32, I think it's perfect. And model.add, now I will add one more convolution layer. I can have many, but it's an image, so I just want a pretty good accuracy, so I'll just use again multiple, and here I can have 128, and again the kernel size is 3 by 3, and then the activation function obviously is relu. Okay, perfect. Now what is obvious after convolution layer? I said it's pooling. pooling layer, and the best way of pooling is max pooling as of now. Any pooling is fine, average pooling, max pooling, but max pooling is most preferred and most used, and it takes the maximum of it. And the pool size I can take is 2 by 2 for the getting the for rescaling it, or for decreasing the spatial size. 2 by 2 is more than sufficient because there are multiple feature maps which are coming into picture here. So I can use my pool size as 2 by 2 to get affect my feature maps. So this is one. Okay. Lastly, I would also add something called dropout. So what is dropout now? What is dropout? And 0.25, 0.5% dropout. Yeah, dropout is a layer which we use to overcome overfitting. Okay, so dropout is what? It helps us to overcome overfitting. So if I give a value of 0.25, that means I am offsetting 25% of hidden neurons output to the next neurons input. Okay, so see, the neuron is able to predict certain outputs in the hidden layers, but I'm offsetting it or closing it or forcing it to zero, saying that you have to close yourself for now and not give your input as you're not should not give your input to next. So by doing this, I am closing some of the nodes in the layer, so that helps to make my neurons learn better. And the advantage is it can't overfit with the exact data. So when I'm closing some nodes, it's not knowing the value of it, so it is offsetting it, closing to zero, and it says, okay, I don't know data, I'll learn it better. So that's why what's happening when you close the eyes of a neuron, then it has to learn it better. It's not overfitting also, it's not mugging up the data. If I say so, I have added dropout to overcome overfitting and offsetting 25% of my neuron nodes. Now let me add more convolution layers. Let me copy this instead of doing it again here itself. So I have another convolution layer, and I can say 64. This is my input layer. Okay, the first is input layer, and this is my CNN convolution layer 1, and this is convolution layer 2. I have given the filters as 128, here as 64. Okay, and then pool size is okay, 2.5, and even the dropout is fine. Okay, so here I have two convolution layers and one input layer. Should I add more? Maybe I'll add one more, and here I'll give 128 again. That should be fine for a better learning, and maybe I'll not go further with it. And now what? Now what? I should now use my the dense layer to sigmoid, right? But before doing that, there's something called flatten layer. So what is again a flatten layer? So flatten layer transforms all these arrays to one-dimensional array, okay, and appends to subsequent rows. So we are flattening all these layers for our predictions and training using a flatten layer. So we're converting all this to one-dimensional array with by adding subsequent rows. Okay, so the thing is model.add flatten. So I'm flattening it now. Okay, and model.add, let me add a dense layer. Obviously we need to show dense layer in the outcome, and I'll add, suppose I can add, because I've added a flatten layer, I can add a dense layer with 64 nodes and relu, and then I'll do a dropout again. Maybe I'll increase dropout for 50% dropout because I've added a dense layer now. And then again I want to now just go to my last layer of the output layer. So output layer should have just one outcome, COVID or not. So one node which says yes or no. The value of this layer should be 0 or 1. Okay, so yes COVID or not COVID, and the activation is can't be relu, it is sigmoid. Sigmoid just gives two values output, 0 or 1, 0 or 1, prediction of 0 or 1. So I have my model ready now. This is my entire model. Input layer, convolution layer 1, 2, 3, flatten layer, dense layer, dropout, again a dense layer with the dense layer of output layer. So this is the output layer with sigmoid function. Perfect. I think it's done. I mean, the model is defined. It's not trained yet. We haven't given the data yet. Okay. Let me do model.compile. So I have a binary outcome, 0 or 1. So I will use binary cross. The losses binary cross entropy. So I better use this losses dot binary cross entropy, and or you can just give loss equal to double quotes binary cross entropy. And the optimizer, in the last lecture I have given double quotes, that way or this way both work. And the optimizer is Adam. So what is an optimizer now? What is an optimizer? Yeah, so I said I will explain this lecture. So it's very simple. So optimizer, so they can change the attributes of a neural networks like weights and learning rates to reduce losses. Okay, so it's used for faster computation also, and faster results also. So the pretty popular optimizer is Adam. So it basically, the optimizer can trigger the learning rate and weights automatically to get the right results and perfect results. So Adam is a popular one. You can use others also, Adam or SGD, stochastic gradient descent optimizer, SGD as optimizer. So Adam, it works better for gradient based optimization for stochastic values. So we are using with Adam currently. So our losses is binary cross entropy because 0 or 1, and optimizer is Adam for better training. And then metrics is, I want to focus on accuracy. Perfect. I have compiled my model. Let me check my model summary. I haven't trained it with the data. I'm just defined it. Perfect. So if I said right, the sequential model and input layer, input convolution layer, and one more convolution layer, max building layer, and the dropout. You can see this. So we have flatten and the output, and you can see the output shape. The output shape of this data is this much and this much, and see this, how many parameters we are using here, how many nodes, how many neurons are getting inputted to it, and what is the size of dense layer. The size of dense layer is 64 and the output is 1. So we have flattened to this shape. You have every detailed information in between the model. Okay, how many parameters are being used, how many trainable parameters are being used till now. It's a bit big data with the data we have of images. Okay, so now we have our model set up. Now let me start with getting my data inside the model. So for that I have to mold my data or mold my images data. So how do I do that? So there is something called image data generator. I think we already know. We have already imported that image data generator in our code with Keras. So for the train purpose, train data generator equal to image data generator of. So I want to rescale my data. I said my data is of 244 by 244 by 3. I'm rescaling it to the right value. So 224 by 224 by 3. It's not 244, it's 224 by 224 by 3. And the shear range, so it's used to, what is shear range? Basically shear range is helpful to get your data with respect to different counterclockwise directions. So the counterclockwise direction we are using is 0.2, and we have zoom range. I'm zooming it to 0.2 again, and then horizontal flip. So that is also required when I keep the image flipping horizontally vertically. So I can just use horizontal flip equal to true, so that it can work with even this kind of data. So this is my train generator, data generator for images. So we are modifying or molding our images according to this. For test, it's not required of all these things. We can directly input it later. We just do test underscore data gen, and I'm just rescaling it to this value because this is the minimum requirement for this. So I have my data here. We have defined our data generators. We haven't molded it, we have only defined it. Now we have to give the data. So now I'll just give train generator is kind of train data gen dot flow from dictionary directory, sorry. And I have my train path, code path. So in this there are two folders. I give my path here, and the target size I need to give is, what is target size now? 224 by 224, batches. See, if you take the whole batch, it will take time, and even your CPU may crash. Crash can stop. So batch size is required to do it slowly and comfortably instead of loading it all together. And the class mode is binary because I have two classes. There are multiple parameters you can choose, but this is the base minimum for my input. Okay, yeah, perfect. This looks perfect. I'll just do the same for my test data also, or the validation data. So I use my test data gen, and my validation data is this. I have two folders. Yes, right. Target size, batch size, everything is perfect. So it says it has 222 images belonging to classes, 60 images belong to two classes. This seems perfect. I think they have taken my data now and also molded it properly. I just have one main thing to do, that is what, to fit my model with this data, right? So suppose hist new is like the parameter I can take model dot fit underscore generator. So I can use train generator as data, steps per epoch. I can take 8 steps per epoch, and epochs is 10 iterations basically, and the validation data is validation generator obviously, and the validation steps can be also defined as 2. So how am I model training here? I'll just, yeah guys, so finally our model has been trained. It took some time because it was complex model, and there are 8 epochs and 8 epochs sorry, 10 epochs, and I mean 8 steps per epoch. So it took some time, and also it was image data, and we had a lot of data, and it was very complex model. As you have seen model summary previously. So it took some time, and finally it is done now in my system. And so this is the output for it, and then also I have got the summary. So you can just check the summary here. I have saved it just before I lose it again. So I just saved it. So I've saved it. Yeah. So let me load the model. I've anyway saved it. I'll just show how to load the model also. It's already saved. I'll just show you where it is saved. So my model is saved here also. So my model is I can load it this way. Keras dot model, sorry, models dot load model. And my model is this. So I have loaded my model. Yeah, it took some time to load my model. So now let me evaluate it. Sorry, where is my cursor? So model dot evaluate generator of my train generator. So just checking my evaluation of train generator. So it's taking time. Yeah, it has come. So this is my train generator value. I have evaluated it. It's I think pretty fine. So now I'll do the same for my validation also. I think it's still taking time. Yeah, it's done. So it's like it is pretty good evaluation, 0.96, 0.95, and 0.045 and 0.059. So I mean it's pretty good as per what we have seen. What we'll do, best thing is we'll apply confusion matrix and just get to know our accuracy, right? I think all of you know what is a confusion matrix is, or I can just show it here itself. Train generator. Let me know the class indices first, 0 and 1, right? I'll just confirm that. Yeah, COVID is 0, normal is 1. So let me do that. So now the output actual is, let me define as dummy. Now I have my data in my validation set, right? To make my confusion matrix, I need to have data somewhere. So my data is already here, COVID and normal, for validation of my accuracy with respect to confusion matrix. So I'll take first normal and then COVID. Okay. So what I'll do, I'll iterate over all the images. Yeah, I have images here. I think around 30 or something. Yeah, around 30. And same thing for this, around 30. Right. For each I think I need to import OS first. For each OS dot list directory of my path is this normal. I just copied it, right? And then image, for each image dot load image of what, the same path plus the image, each image, right? The target size obviously 224. We have already remembered that, 224 by 224. And then image, I need to expand it for better results. Expand dimensions of image equal to 0 axis. Okay. And the prediction is model dot predict classes 0 or 1, right, for images. And the y test, I have defined y test here empty. So I'll let me add y test for this. Y test dot append my prediction of 0 comma 0, sorry 0, yeah, 0 comma 0 only, because we are having multiple here, and the actual is already known to us. Y actual dot append what, obviously 1. This is normal is 1, right? So actual is 1, amperated is here. So I have two lists, y test and y actual. I'm iterating through all my normal photos of or scans. I'm just loading them, expanding dimensions, and predicting each image, 1, 2, 3, each image, and the value is in y-test, respectively. And we already know y actual is what, 1. It's COVID. So it's normal. Normal is COVID. So 1. So y actual and y-test is appended properly now. I mean, respectively properly, right? Let me copy this. Okay, there's some issue with the path. Error, no such file or directory. COVID. Okay, I think the path isn't proper. Where, which, here, load image. Let me take an image. Slash, perfect. I think slash was missing, and I have added slash. I think it's done. I have y test and y actual for my normal. Let me do the same now for my COVID photos or the COVID scans. Okay, for each I'll be adding and trying getting the predictions, and also I have actual as 0. Actual is 0, right? So I'll just see y test as 0 and prediction is this. I just need to change this path as COVID. Recently, even I got COVID, and I was well soon. Even they didn't X-ray to me, but now I understood what's the difference between the X-rays here. So I have it on proper, right? Prediction is 0. Appending is 0. I think this is required. This is done. So it's almost going on. It's done. So I have my length of y actual and y test. We'll just see. It should be 60. Perfect. And length of y actual is 60, obviously. So, and if you see y actual, it should be 0 and 1, obviously, as you already know. It's 0 and 1, first ones and then 0, so totally 60. Perfect. We already got the predictions also. Let us see the y test predictions, and then let us do the confusion matrix. Perfect, we got the y test also. I think maybe some errors is because 1 1 1 1 0 0, there's some errors between, but almost I can see it like 90% correct for the validation data, right? Perfect. Now let me make the confusion matrix. I think we already know how to do it. We'll convert first the y actual and y test to a numpy array. Perfect. So from this, now let us use confusion matrix. So sklearn is a library where we have confusion matrix defined. Import confusion matrix. Perfect. And I want Seaborn to show visualizations. Import Seaborn as SNS. Now my confusion matrix CM equal to confusion matrix of y actual and my y test. Okay, and yeah, SNS dot heat map of my CM comma CMap value can be plasma. Okay, there also okay, I not is true for 0 and 1s. Perfect. So I got a heat map with all the results. So I have 60 images in that 30 plus 0. So I mean I've seen here, right, the y actuals. Let me see, show that. Yeah, let me do it here. You see, I have COVID 0. So 0 0. So out of 30 COVID images, all were done correctly predicted. Out of 30 normal images, it says 28 were done correctly, and 2 were shown wrong as COVID. So I think it worked perfectly. There is no false negative at all. That is the greatest thing. There is no false negative value. We have, or maybe you have some false positives, but that is fine. Just two. We have almost like more than 99% accurate result for 60 results. Out of 60, 58 are correct. We have an exact prediction of our model. So our model works pretty well with the confusion matrix. So I think this is a perfect result we have got. Just with 220 images, I was able to generate these results. If I want to do for a particular data, then let me do the same. See, even if I see the y test, only 2 are wrong. Here it is 1. So I think only 2 are wrong. The y actual and y test reveal it completely. And let me copy this, and let me see for a particular image. So my image is 224. Let me remove this image folder, and let me take a specific image. I have a test, right? So I have 4. So this is a COVID image. I'm hoping so, because this white color and black color combination shows that there is some issue here, and here also some issue. Here there's no issue. Everything is visible clearly. This is also clear. So I think these two are normal. These two are COVID. So I have a data, some real-time data here. So I'll just copy this path and paste it here, and let me see what it says. It says 0. It's COVID. Perfect, man. I have created this, and it's COVID image. So for a single value predictions, it's working. And let me take a normal image. Let me give this also and just check it out whether even normal is working fine now. Perfect. It says 1. It says normal. So I think our model is working pretty fine. So what we have done, to summarize, we have developed a CNN model to detect COVID based on the lung X-rays. So we have implemented a detailed CNN model with all the proper inputs, all the proper parameters, all the perfect layers. I had taken 3 CNN convolutional layers, 3 max pooling layers, 1 dense layer, 1 flattened layer, and multiple dropout layers. As you have seen already, the summaries. So this is my model summary, and I have trained my images, actually molded my images and trained them. So I have a perfect result for it. Okay. So this is how the CNN works, and it's able to auto identify features. I didn't give the color combination anywhere. the ribs visible, or the whiteness, or the whiteness here, the ribs visibleness in here. But I can see that this can be COVID, this can be COVID, but this is not COVID, this is not COVID. How do I see? There is something going on in my brain, and I'm able to analyze. The same thing, even the CNN model is doing, it is able to identify features based on these combinations and trying to predict based on the trained data and show results for my test and validations. Right. So let me summarize before that. Short summary. So what I did from start firstly. So I have imported all my libraries. If I see the Keras model, the matplotlib model, I haven't used this model actually. It's not required. I can remove it because it's not used. I have used Cborn instead of this, and I have imported my model. I mean all my libraries, the Keras libraries. I have defined a sequential model, right? And there's a convolution layer one. I mean, so input layer and the convolution input convolution layer with 32 filters, the nodes, and the kernel size of 3 by 3 for mapping it or doing the convolution of these two. And the activation is relu, and the input shape is this. The image shape I have defined it 224 by 224 and by 3 because the kernel size is 3 also. I have given it 3. Then again one more convolution layer of 128 nodes and same kernel size, and the max pooling layer, the pool size, to decrease the spatial size of each feature map. So I use 2 by 2 to decrease or downscale the image data. Okay, and the dropout is 25%. So I'm closing out 25% of my nodes. This is an important part of my complete CNN presentation, because this is how actually you build your basic structure or the summary of your model. Okay, and then one more convolution layer, and then flattening it. So what is flattening? So getting all this data into one dimensional structure, subsequently into rows, and then the dense layer using relu, and the dropout layer 50% nodes I'm dropping off, and the dense layer and sigmoid, obviously sigmoid, so sigmoid to give the right classes 0 or 1. Then I'm compiling it. If you have seen, then summary, you can get a detailed view of what is the summary, how many things are being used in the summary, the parameters and all these things. And the main thing is I have defined my model till now here, as you have seen, and here I have molded my images, rescaling it. Shear range is what? Counterclockwise directions 0.2, and zoom ranging 0.2. Horizontal flips considering true. Okay, if there are horizontal flips, then it can be considered. And then the test gen, I haven't done anything because it's for the validation. We haven't used it. And the train generator and validation generator, here is a part where I'm giving my data or the image to the train generator and test generator. Okay, so that is how I created this data, and it is seeing 220 images and 60 images, and you can verify our data set. It will be the same, 220 plus 60. So 220 is my training and validation is 60. We have also verified that 60 was perfectly working. And then let me go through fast down. So I have evaluated my train generator and validation generator. It was pretty perfect, and the class indices were 0 and 1. COVID is 0, normal is 1. And then what I did, the main part was to do my confusion matrix. I have appended the y actuals of both and y test of both. I have of the all the validation images. I have tested all the validation images, iterating it for each, and then appending it to y test. And then if I check, it is 60 60. Y actual is also correct. It's actual is 1111 obvious. And y test is 0. There are 2 errors, but it is still 99% accurate, if I can say. And then after that, I have done my confusion matrix and then showed the heat map through this, and you can see that there are no false negatives. There are 2 false positives, but they are not effective. So what is false negative? See, saying that a person has no COVID even though he has COVID, that is dangerous. That is false negative. I haven't had this case. It is 0. But there might be a case that a person doesn't have COVID, but I may have said that he has COVID. That's not a different case, because actually he doesn't have, but I have said he has, maybe based on certain model thing. But still there's no issue, because even if he again rechecks it, it will not be there. So that is not an no big issue, because it's a false positive again. So there's no error. And 30 plus 28, so I have accurately set 58 out of 60 are perfectly classified based on the image data. And then I have taken 2 images and then predicted each of them. So you can give me your lungs scan, I can just put the image here, and I can say whether you have COVID or not. That is the level we have developed to, and accurately it said that it was perfectly working one.
If you're learning about neural networks, you're probably someone who wants to be the master of analytics world. Join our postgraduate certificate in machine learning and deep learning by IIIT Bangalore at upGrad and gain the skills employers are looking for. With a practical industry-aligned curriculum and hands-on project, You'll not only learn from the seasoned experts, but also apply your knowledge to real world scenarios. Don't miss out. Click the link in the description to start your machine learning journey today.
In the last sessions, we have discussed on neural networks, what is a neuron, what's a neural network, what's an ANN, what's an CNN. We have also implemented many wonderful use cases on predicting the diabetes in a person or COVID in a person. We have trained such models using CNN and ANN and also got a brief of all the networks, neural networks. Right. So here in this session, we'll be going to discuss on RNN. Okay, it's called RNN. So RNN is a special type of neural network, I can say. So okay, obviously there are a lot of neural networks in the market. Why this is required? Why RNN has required? And why it has got its importance? Okay, so in this session, I would say what is RNN, why it is required, how does it work, its uses, and the problems with RNN, and then how to solve the problem with RNN. It's by LSTM. How does it work, and its use case. We'll be implementing some wonderful use case with LSTM. Okay, so what is RNN? So the full form, if I say, it's recurrent neural network. So recurrent, the reoccurrence, that is a completion, recurrent neural network. So it is very significant. So based on reoccurrence of an output as an input, this model has formed. Basically, this algorithm has formed. Okay, why actually it is required? Basically, how does it work? Yeah, so it works in such a way that it saves the output of a particular layer and feeds it back to the input, and in order to predict the output of the next layer. Okay, so it is trying to loop it over and say what is the next output, not is the next output, and every output is again an input. Every output is again an input. Okay, so what is the use of doing such thing? What is the use? If I say X as the input layer, here H as the hidden layer, and Y as the output layer, the Y output is again given as an input to the X, and again train, right? So here the model is actually becoming time dependent, and even the sequential data problems are resolved here, if you see. Okay, I'll give an example how it can be used. Suppose if I'm training some paragraph, if I say about Raju is a person. So Raju is a good boy. Raju is going to school, and Raju and Ravi both go to school by bus, and Raju is a topper again. So here, if you see, the context is completely about Raju, and Ravi can be ignored actually. It's a small thing about Ravi. Raju is important. And second thing, there are a lot of attributes which are updated in your mind of Raju. If I say Raju is going to school, you say that he's going to school, and he's going to school by bus, and he's topper. So the context is being understood of Raju only. So when you're training such a thing with the network, you need to give the features of Raju to the network. So you'll be adding one by one, updating one by one all the features. If he says tomorrow that Raju is now 5 years old and his school got over, then we are updating again. Raju is now not a school going guy. He's an elder guy. He's an elder. Okay. So such a way, if you want to train and also update the context, or increase the data of the context, such a approach, if you want to go, you have to use RNN, where the memory is being stored. Okay, the previous memory of the trained data is being stored. So that is the advantage of using recurrent neural network, RNN. So, if you say a specific use case like machine translation, suppose if I convert machine translation problem from Hindi to English, suppose. So in Hindi you may say शीला अच्छा आदमी है, वो कह रहा था कि सब लोग भी अच्छा होना चाहिए, suppose some random example. Okay, so here if I want to translate this to English, you say she is a good person, and she, वो कह रहा था, बोले तो what, she says everyone should also be good. Okay, so wo is trained as what, she. I have actually trained manually as she. Now I again give one more data. Raju बहुत अच्छा आदमी है, वो कह रहा था कि सब लोग अच्छा होना चाहिए. So here again वो, if I translate to English, it says Raju is a very good person, and वो, he says everyone should also be good. So when I train wo in English, it can be it can be he, it can be she. But Hindi, wo means it is both, she also, he also, it also. But the machine will not understand all these things. Only when you give the old input and again retrain with o with different examples, with different uses of wo and different context around, with Sheila, with with Raju, different context, then it understands the wo has a different perspective in English and wo has a different perspective in Hindi. So it can be used common way. Okay, this happens only when you retrain, when you reason. Just like a small guy, small child, if you teach him some language based on number of examples he's trying to learn and updating his language context. Even if you go to a new place and want to learn a new language, initially you may say ti ta, and no, in Hindi, like ti, people say ti instead of ta, they say ti. I mean, they don't know where to use ti and ta at the end of the sentence because they don't know the context. But as they learn and update their context, they can understand, okay, this is different from my language, Hindi is different, and here I can translate as that directly like this. Okay, so that is when you want to memorize the old data and also train on multiple contexts, then you use RNN here. So basically RNN, it has the time factor in its picture. At any given time, the current input has a combination of input at time t and t minus 1. If I say in technical terms, at t and t minus 1, it has the combination is the input of t and t minus 1. If I just say, at every point, it has a context of t and t minus 1. If you see this image, and at the output at any time is fetched back to the network again. So the two things, if you say of RNN, that is at any the output at any time is fetched back to the network to improve on the output. Okay, that is first thing. And second thing, it has time factor. If I say the current input has a combination of input at t and t minus 1, that is when you can say if these two cases are accepted in the network, then it is an RNN, recurrent neural network. And why it is required? Obviously, the feed forward networks, the normal feed forward networks cannot handle the memorizing things. They can't handle sequential data. RNN can handle sequential data. So the advantage, if I say, can handle sequential data, and then it handles data at different times. Basically handles current input at different times. Even the old data basically it can handle, and it can memorize previous inputs. This is very important. It can memorize previous input. So that is why people have actually gone mad after RNN and LSTM. And if I say use cases, there are many use cases which are actually going on with RNN. Okay, the image captioning based on the activities in the image. Okay, that is a RNN problem where different activities show different contexts. It can be sunny day with a person which is sitting with his girlfriend, red dress, and in the park. So there are different objects there. Based on those objects, training them again and again, you can predict certain caption to it. Okay, certain caption you may write it, RN can understand this caption based on the image. Okay, and or if you take an image with crowded people in the market with lightings and some dharna and some people selling some things, then it's a festival environment. Okay, so it can auto captionize things based on the activities in the picture, because there's a lot of data being updated every time based on different scenarios, the background, the lighting, the color, the people, the crowdiness, the things they are doing, selling. You can say that what is happening there, right? So every time the object is being updated. And the time series prediction of stock market. See, if you want to predict any stock market, it is obviously dependent on previous data as well, right? You can't predict a stock market based on single data. So you need to have the previous data. Stock market prediction is a very important use case if you want to go with RNN. And then NLP, text generation. Now you might have heard of TensorFlow for poets, or the poetic generation. So even the machines can generate the poems of Shakespeare, similar poems like Shakespeare. How? We are training the machine on the Shakespeare data, poems data, and it can, if you ask any context, it can give you a similar context, right? And then, or you can even continue the story of if you train with some paragraphs. And then machine translation. If I already gave an example of this machine translation. So there are wonderful use cases with RNN, because everywhere people want the machines to remember the previous data and take decisions accordingly. Okay, so some I'll just mention here: image captioning, text generation, machine translation, time series predictions, like stock market. So this is how RNN helps us in various scenarios. So we have discussed what is RNN, why it is required, how does it work, what are its uses, right? I can go a little bit deeper. So this is a sample RNN, so that data is being fed back again and here again. So now, as I was saying, what are its problems, why people have moved to LSTM compared to RNN, direct RNN. Basically it has two problems. One is vanishing gradient and exploding gradient. I've already explained what is gradient in the previous lectures. Just go through it. I'll explain what is vanishing gradient and exploding gradient. It's very important. Anywhere now you go, if you say people, neural networks, or even if you know RNN, they ask you these two questions only. If I say people want you to know these two guys, what is vanishing gradient and what is exploding gradient. Okay, I'll explain that. So in the neural networks, you already know there's a lot of gradients involved, and based on which the maxima, minima, and the training process happens, right? So here, while back propagating the data, so obviously the back propagation is there, propagating the data, the gradients carry information, okay, needed in the RNN. So the gradients become too small. So if I say this, based on T, the data is being back propagated to retrain and reduce the cost function. If I say in the previous lecture, I've shared what is cost function and what is gradient and everything. So just go through that if you're not sure what it is. Okay, so to reduce the cost function, to reduce the cost, minimize the cost, or minimize the error, or minimize the bias based on adjusting the weights, we need back propagation, and then again sending it to train based on the epochs, right? So if I send back propagate, what happens in RNN? It goes throughout the network as an input again, right? So if I say it goes back, it goes back, it goes back, it goes back, right? So what happens when it goes back to long instances, long term? Every word, if I say wo kehta hai, he is saying that, he also says that, every word is actually fed as an input. Even from the output, every word is fed as an input, and again from the output, every word is again updated, right? So when it is being back propagated, the gradients which carry information, okay, the gradients become too small. Okay, suppose the gradients become too small, it will become like, obviously gradient is what, the dou by dou, right? Dou by dou. So when you do dou by dou, it becomes 1.1.0000000. The gradients become very small and become insignificant. 0.00000. So when you're sending the data, send the gradients back, the weights, so it is getting back to the network to adjust itself, to adjust the weights, to adjust the error. So but the problem is when you do dou by dou, so the gradients become small, they become 0.0000001, and they become insignificant. So then such long sequences cannot be learnt. When they are not being learnt, then there's no point in training RNN, right? So that is called vanishing gradient. What is vanishing gradient? When in back propagation, when the data is being sent back as a with the gradient information, they become too small, very small in the long sequences, and they become insignificant. And because of that, there's no point in training them much. It is not learned properly. That is why the RNNs have certain issue with vanishing gradient, because the learning isn't happening properly. Okay, so that is the first issue, vanishing gradient. The gradient is slowly vanishing. Second issue, this is more dangerous, exploding gradient. Okay, exploding gradient, even if it is vanishing, it is not able to learn. There's no problem. But if the gradient, when the gradient is exponentially increasing, when it's sending as a back propagation, the gradient information, when it is sent back, it is, what is happening? It is trying to update itself. It is trying to send through the network through long sequences, but the problem is not vanishing now. It is increasing. The weights are increasing. The gradient is increasing. It's lot. If it is not, it's not 0.1. It's like 100, 2000, 10,000, 1 lakh. It's continuously increasing. If for a long sequence, it increases more and more. It's exploding gradient. When it's exploding, what is the issue? It will have larger weights, larger errors. It will take longer time to train itself. What is the problem with long training? Poor performance, bad accuracy, right? So this exploding gradient, because of this back propagation error, when the data is being sent back and being exploded, the gradient is being exploded by the carrier of information. The data is the training is becoming a problem because of long training, bad accuracy, exploding of gradient, bigger weights, and the updates is not happening properly during training process. So that's when the network breaks. Your training breaks. That is called exploding gradient. So vanishing gradient and exploding gradient are the biggest challenges in RNN, and that is what have made them flop. Okay, I hope Guys, I've explained what is RNN, why it is required, how does it work, the problem with RNN, its uses, everything. Right? I hope you're clear with this basic understanding. Now, how do you solve these two problems? Because of these two problems, I can't ignore RNN because it has a wonderful importance because it can memorize my previous inputs and give me the right decisions based on my previous inputs. So I don't want to lose this advantage based on these two problems. That's when a special type of recurrent neural network has come into picture called LSTM. It's called long short term memory. It's called long short term memory. I'll explain this. What is long short term memory? I have popular link which is a relevant link for LSTMs. So cola.github.io. I'll go there. I'll explain this article itself. It is very famous link, very detailed. You can keep it as a reference for your future learning on LSTMs also. I'll go through this link itself and explain you how LSTMs work now. Okay. So what is the difference between LSTM and an RNN? We have a problem in RNN, the exploding gradient and vanishing gradient problem that is overcome in LSTM. And how does this handle that? Compared to any neural network, LSTM has three structures inside. It's not one; it is three structures. Okay. So if I take an example, the clouds are in the what? Clouds are in the sky, right? So if I take the example, the clouds are in the sky. So sky is the predictable object. So it's easy to say, clouds are in the sky because the clouds are here. Based on this context, I can say sky can be the answer based on my training. Okay. But if I take a sentence like this, I grew up in France and so and so I did this, that, and finally I ask, I speak fluent what? French. How do I get it? Obviously, the context is about France. I have been grown up in France and I did a lot of things in France. So I can say I can speak French very well. Based on the context of France, I can say French as well. I can't say Hindi, I can't say English or Spanish. I can say only French. This prediction comes right when I understand this context. That's what RNN do. RNN actually understands the previous data, the clouds, it understands and say sky is the answer. The France, it understands and say French is the answer. That's what RNN do. But the problem is, how much data can I remember? I just wrote I grew up in France. I wrote a lot of unworthy data, X, Y, Z, A, something, whatever. And then lastly, after long data, I say I speak fluent what? French. So do I need to remember all the unnecessary data in middle? I grew up in France, etc. X, Y, Z, what to do, etc. And say that if I ask French, do I need to remember all the unnecessary things? I just need to remember France, and then based on this word or this context, I should be able to say French. But the problem is RNNs have long dependencies. Because of long dependencies, they are having issues. So now LSTM, it says, oh RNN, you are useless. You are unnecessarily remembering everything. LSTM say, I am better than you. I need not remember everything. I remember only what? Relevant, recent information only. Okay. So what is LSTM? They are similar to RNNs, but they only remember relevant information. They don't remember anything else compared to RNN. That is how, by remembering only relevant information, it is able to train faster, compute faster. It is able to overcome the vanishing gradient problem, overcome the exploding gradient problem. Okay, that is how it is lot better than LSTMs. Okay, so a lot better than RNNs. LSTMs a lot better than RNNs. So because they avoid the long dependencies like RNN, they only remember the relevant information. Okay, but compared to any neural network, they have multiple things in between happening. It is not just one component. There are three components happening in LSTMs. Okay, if we consider this block as a cell state, C t minus 1 as the cell state at t minus 1 and Ct as the next cell state at time t and t minus 1. Okay, so the LSTMs have three things working inside that. One is the forget layer, and then the input layer or the update layer, and lastly the output layer. Okay, the LSTMs have these three things, three functionalities happening inside compared to RNN. So what it is doing? Forget layer. It forgets unnecessary data. Second thing is update layer. It updates new information accordingly or adds new information accordingly. And finally, output layer. It filters the right information for the next. It filters the output. Okay. So what is happening here? Firstly, the forget layer. So sigmoid function based on the previous inputs and the new input, it is trying to forget the old data. The sigmoid function, it's a sigmoid layer if you see. So sigmoid layer what? 0 or 1. It chooses the output between 0 and 1. right, of the cell state, and says, should I completely ignore this data or should I completely add this data? Okay, so it is forgetting unnecessary data. So that's why we have only sigmoid layer here. Suppose no, I gave an example. I have an example. Suppose Sheila is a very good girl. Sheila and Raju go to school by bus. Raju is very good boy. Raju goes to school by bus. Raju is topper of the class. If I say all these things, firstly, when I give data, Sheila, so I spoke about her, she, so gender is she. Sheila is a very good girl. She goes to school by bus with Raju, and I say about Raju. Raju is very good boy. He is the topper of the class. He's a very good student. So, firstly, the gender was about Sheila. The subject was about Sheila. Gender is she. But now, currently, I'm speaking about Raju. The gender is he. I need not remember Sheila, which is she. The gender has changed. The gender is he now, right? So the forget layer understands that the subject has changed from Sheila to Raju now. So the gender has to change from she to he. Okay, don't take it wrong way. I'm just speaking it via the context. So it has what it is doing. It is trying to forget unnecessary old context and consider only the new context of Raju. That is what LSTM is doing in forget layer through the sigmoid layer. Okay, if you see the function, the same thing. st minus 1 into xt, the old data into the new sentence with the weights, so, and the and the bf with, okay, choosing what to forget. And next is what I said, update layer. Three things. First is what? Forget layer and the update layer, or the input gate layer. So it has again two things, the sigmoid and the tan h. So tan h is between minus 1 to 1, sigmoid 0 to 1. So here what it is trying to do, the LSTM using this layer, it is trying to update the information of the current subject or add new information. So I was speaking about Raju. Raju is very good boy. He goes to school by bus. He is the topper of the class. He is very intelligent. Suppose so. All the old new data of Raju, intelligent, topper of the class. These are all the new data of Raju. So those things should be updated on the Raju's features. So that is happening through tan h and sigmoid. So where the sigmoid is considering what to update and the tan h layer is considering what to add. So sigmoid is what to update. What should I update now? What data? And tan h, is there any new data adding on? Raju goes to school by bus and Raju and something else also. So what new data has come into picture? New data and updating. That's what happens in this layer, update layer or update and add layer or input gate layer. Okay. And then they are merged here. Then they are merged here. The forget layer is merged here to the cell state, and the update layer is merged here to the cell state. CT minus 1 is old cell state. CT minus 1 is the old cell state, and the forget layer is merged here. The update layer is merged here to the new cell state, CT. Okay. And then what? There's one more layer. If you see here, the third one. So what is this? The output layer. The output layer of the LSTM. So here again we have sigmoid followed by the multiplication of tan h. Okay. So firstly, what we are doing in this layer is we are filtering out the required data. Sigmoid again is 0 to 1, right? So it is here we are filtering what data should be sent as an output. Okay, is everything need to be sent or not? Okay, so maybe like there may be some data, unnecessary data. Some data may be relevant. Maybe the gender or singular, plural, all these things might have been updated of Raju. So he says they go to school by bus. So the data has been become from singular to plural. So that is an relevant information. So it passes through it and multiplied with the tan h function. The filtering from minus 1 to 1 only will be sent to this parts of cell state. So basically this output layer is a filtering layer of the input. Okay, filtering layer of the input. Okay, so that's when based on the forget layer, output layer, and the update layer, we are considering the next cell state. Okay, so that is how LSTM works. I can take an example. So firstly, I talk if in a paragraph the data is about Sheila, and then I speak about Raju. The gender has been changed, so the forget happens of gender, and the update I gave more information on Raju. So the gender has changed, updated, then added more information of the subject Raju. Raju goes to school, topper, and then filtering out if the context is about singular, plural example. So based on that, I choose the filtering option, the context filter, the output layer, and then based on these three actions, I combine them and show to the cell state, next cell state, and this cell state again adds the new input and again goes as an input here. Okay, so every time the input has been adding with the old input, old output. So that's how it's able to determine and forget unnecessary things and remember only relevant information. So what is the goal of LSTM? To avoid long dependencies and remember only relevant information. That's why it's called long short term memory, LSTM, and that's how we are able to work better than RNN through LSTM. Hope LSTM, the theory or the concept is clear. This is very important. You can keep this post as a reference for your for your learning. But this is how LSTM works. Now let us go through a use case. Let's consider a use case. So with LSTM, I want to predict or text generate the writings similar to the famous writer Edgar Allan Poe. So basically, I have a data set which is part of Kaggle Spooky Author Identification. So this is the data set. Okay, it's downloaded from Kaggle. Okay, and the data set name is Spooky Author Identification. So this data set has a lot of texts of different authors: EAP, HPL, MWS. So basically, this is a short form. EAP is Edgar Allan Poe, HPL, MWS, and a lot of writers are there. So based on their writings, they want to predict whether this text is written by EAP or HPL or no MWS or whatever. Okay, but I am not using this for text classification, but I am only filtering out EAP. EAP is what? Edgar Allan Poe. Let me filter it out here itself. So there are 3 authors. So I have only EAP now. Edgar Allan Poe dot text, author text. So there are almost how many? 19,578 records. Okay, for this author itself. So I'll just capture this data only. Okay, and I will be able to generate similar text like Edgar Allan Poe. So if you read that text, you will say you may say that this is exactly maybe written by Edgar Allan Poe only. Okay, maybe he might have written this text, but actually this is the I'll be generating text which is written by machine based on giving this input data. I'll be training the data on these terms and then generating next words based on this. Okay, this is called basically text prediction, text generation. So based on certain wordings, I will be able to predict the next word. Okay, but I am taking into consideration EAP only, Edgar Allan Poe, and I will be trying to predict the text. So my use case is what? Using LSTM, I will generate the writings similar to that of Edgar Allan Poe. Okay, by training his data set only, by training his words only, by training his writings only. Okay. So I'll be using LSTM. I'll be using Keras. Okay, the data set is Kaggle Spooky Author Identification dataset, but the use case is a little different. Text generation. Okay, so by standard data science libraries for this use case, I'll not explain this in detail because in the previous lectures I've already explained why I'm importing what and what is the use of each. Okay, so I'll not be explaining them. You can just go through them if required. Okay, but I'm just pasting it here. Libraries are default here. Now I'll start. Now I'll start loading my data set. My training data frame equal to pandas.read CSV, and my data set is already here, train.csv, and but I am only selecting the data of whom? EAP, Edgar Allan Poe. So I need to filter the data frame by EAP, right? EAP. I just take that text. So now my data set is this author. I have only text of EAP 19,577 with 19,578 records, as we already seen in the CSV. Okay, now just let me check the shape. In that case 7,900. So the words basically, if I take the author shape of 0, yeah. So now the max. So obviously, so I'm training a model. So the number of words I want to do is by tokenization, because text data I need to use a word tokenizer. I need to do text embedding, right? So I'll do tokenization, converting the words to tokens. So then if I say tokenize, I need a tokenizer, right? So my sample tokenizer is tokenizer of number of words I'm considering is 50,000 maximum, because unique words should be 50,000. I'm keeping a limit for now. And then tokenizer dot fit on my dataset, right? Fit on texts on author dot my values. Yeah. And so I have all my tokens now. I'll just show it in sequence, because we need to know what is this token. This is 1 or 0, 1000, whatever. So sequences equal to tokenizer dot text to sequences of author dot values. Okay, so what I did now, I did tokenization. So basically I'm converting these words into tokens. So every word is a different token. So if there are 10,000 words, 10,000 tokens, whatever. So if a word is repeating this, then it has a specific token. So I just took maximum 50,000 words to tokenize, and then fit on text, then the sequences, because I need to print the sequences accordingly, right? If I print my sequences now, top 5, so these are my top 5 sequences. 19 to 39 80 is my first sentence, 0th sentence. So just took my top 5. We have sequences ready. Now I'll just do flattening of it. So let me take it as text, the entire flattening. So for each item, I'll take a list for sublist in sequences for each item in sublist. So if you see, there are sublists 1 1 2. So each list is again a part of multiple lists. So I'm just taking the sequence. So I just have my text. So length of text, if I see, so my complete text length of 19,000 records is 2 lakh words basically. Okay, so I should consider a vocabulary size to train my model. If you have already seen the word embedding, so it is tokenizer dot word size, word index, sorry. So if I just check my vocab size now, I have 15,713 vocabulary words. Out of 2 lakh words, only this 15,000 repeated multiple times. I'm flattening it as text, and my vocab size is 15,713. So that's how I can determine my vocab size now to train my model. So 50,000 is large high because it is just 15,000 now. So now based on some 19 words or 10 words, we can predict the next word. So let me consider sequence words. So if I take 5 words, I should be able to predict my 6th word. If I take 10 words, I need to predict my 11th word. So let me take a number of words to train on. So what I'm doing is I want to train 19 words to predict my 20th word. Okay, so this is the way my my model will take every 19 words and take the 20th word, again 19 words, 20th word. So it's like taking a window size, 19 19 19, and next word, next word, next word. So that is how it is trying to predict. So I've just taken a random number as 19. Okay, and I'm trying to predict the 20th word. So 19 is 20 because for faster training, because if I take just 5 or 2, it's like it takes more time. So 19 is fine enough. Yeah, so let's continue. Let us do model dot compile loss equal to. So previously in the last lectures we have discussed about binary cross entropy. Here we have categorical cross entropy. Okay, because it's not just 2 outputs. Okay, and it is not sigmoid, it is softmax, because there are multiple. See, sigmoid is for what? Just for 1 0 or 1 output. Okay, but softmax is for multiple, not just 0 or 1. It can be multiple categorical output. So because we are trying to predict the 20th word, so the word can be anything. So it is just categorical cross entropy. Okay, for the loss, and also softmax for the multiple categories. Okay, but still softmax is a classifier. It's a softmax classifier we are using. Okay, and the loss is categorical loss entropy, cross entropy. And optimizer is obviously equal to Adam, and matrix is accuracy. I think it got stuck. Just a minute, I'll just run it again. Text, vocab size, sentence, sequence length, and then the reverse word dictionary word map, the train and y, x and y, model summary, and model compilation. Compile is missing one argument. Optimizer. Okay, fine. And model dot fit. So we have np dot array. Of train underscore x, right? X, and again np dot array of train underscore y, and then what? Also we need to have dummies. P dot get dummies of. See, the dummies are required obviously because we are having categories like one hot encoding we are using. You might have heard of one hot encoding. So get dummies is similar as one hot encoding. Okay, and then we need to fit on x and y, and batch size is 128, and epochs maybe 30 epochs. So I'll just not run it currently because my kernel got stuck. I'll just run it and pause it for some time. Thing is, it's running. It is not having any error. I just interpreted using keyboard. Okay, but I have a model already saved, so I'll just do that. Model dot load weights. Okay, I have a model already saved here. I'll just use the same model instead of using any other things. I'll not waste time in training currently for now. So I loaded. Okay, so actually my model has been trained and loaded now. Okay, so I just need to now test it. See, I'll just do a summary before I go further. So what I did till now, I wanted to predict or generate text similar to the writings of Edgar Allan Poe. So I will import to my libraries, and then I have read the train.csv. I have filtered using EAP. I got my text. Then I have tokenized it. Okay, to text to numbers, and then I just printed it, and then I seen my text vocab size, so it is only 15,000, but I have given maximum 50,000, so it is fine. And my complete text words are 2 lakh. So vocab size is different from total text. Total text is how many sentences are there. Vocab size is there might come in 100 sentences, but I'm considering only once. Okay, so vocab is of the is not 100, it's one. Okay, and sentence length, I'm trying to predict the 20th word based on 19, so I'm having a sliding window, and I'm doing the sequential operation. I got my sequence, and then I have implemented my uh, model, I mean sequential model. So where I have my embedding layer firstly, an LSTM layer secondly, and then the dense layer, thirdly dense layer, and then I have used softmax function to get my categories, and model.compile, model.fit, and then I have trained my model, and now I have my models loaded. Okay, so I have my function ready to predict. So instead of rewriting it, I save time to just do the prediction operation. So this is my generate function. So I just have a model ready. I just input my model. So generate text of my model, comma, sequence length is 50 and max length is 20. So sequence is what? So author dot ilog of some random. I'll just take author dot ilog of some random text, 907 suppose. So what is author dot ilog of 907? Yeah. So with it came the sense of elasticity and of light. So that was my starting sentence. Okay, and then if you see my after that, automatically the model has given the next words. With it came a sense of elasticity and of light, who indulge in the snore crackling times, presented an altitude of so me epoch so this, if you see, this wordings actually seems similar to that of EAP to a certain extent. Based on a training, we have bought it to some extent. Based on improvisation of training, it will improve more lot. Okay, let me take some other example, maybe some other thousandth line, any word 40. Okay, so let me see 1040. So the actual line is this one, when he had gone and so. So when he had gone and so instruments, and then rambling her entities. So this is trying to predict the words after this sentence, similar to that of Edgar. Okay, so we have built an LSTM model, if you see, where we are able to predict the next words based on the similar writings of EAP or Edgar Allan Poe. So that is how we have finally implemented this LSTM model. Just have the reference of this. So the main model comes into picture here. So everything is text processing except the tokenizations and the model. So this is the main thing. The main thing of LSTM lies here. Embedding LSTM. You can add more and train it more. Thanks guys. I think it has helped you a lot to try to understand LSTM and how we were able to generate text. We are able to generate poems. We are able to write writings similar to the author. Right. Good luck. Have a practice and you'll have wonderful opportunity in this domain. Thanks guys. So in the previous lectures, we have discussed on various topics, right, of neural networks. What is neuron? How does it work? What is perceptron? What is ANN, CNN, LSTM? Everything. We have also implemented sample use cases with respect to that. Here we are trying to understand this hype word called BERT. You might have all heard of BERT to a certain extent, right? So what is its importance? What are BERT transformers? What is BERT embedding? Now compared to any word embedding or word to X. So we already know about word to X, globe word to X, and normal word to X, right? So what is the reference of embedding? What are these transformers? Obviously, we all know that they are used in very nice applications like neural machine translation, text classifications, or text summarizations, and all, right? Even LSTM, in one case, we have actually seen that it's good to work with NLP tasks. Yeah, but what is BERT then, right? So basically, even though we go with LSTMs are not still proper to a certain extent. There are actually better ones. Okay, so LSTM also has problems. See, that's when the progression happens from one model to another model, one architecture to another model, where you find the loops and you want to make it better and better. So LSTM, in one way, if I say, it has also problems. LSTM, firstly, it is slow. So if you see LSTM, actually it is slow. And secondly, it is not truly bidirectional. So even though there is a concept called bi LSTM okay, where it learns from left to right and right to left of a particular paragraph or sentence and try to understand the context, but still it is not proper. So when it is going from left to right and right to left, it is trying to connect those words. I mean, it is actually trying to it is actually trying to connect those words, and it's actually missing out the real true context. It is not it's not happening properly in good understanding. Suppose if I say, what happens is, if I say I'm eating an apple, okay, and there's another word called apple has released a new iPhone, okay. So in this apple, the words are same but the context is different. But if they come in a particular sentence, I am eating an apple and watching my Apple phone, so it misses the context. It is going from left to right and right to left, and based on certain words it's trying to miss the context, okay. So it is not very ideally good at understanding, okay. It is not, as per the market scenario, it's not so good at understanding. It can understand better, okay. So that is why people, these transformers of like like BERT have come into picture, which are already having a lot of good embeddings in it, okay. So what are transformers? Transformers are very fast. Why? Because they're already having pre-trained models and they're already fully connected layers which are there. We just need to work with the output layers, layers, that's all. Already 90% job is done. That's why they're very fast. And secondly, they are truly bidirectional. So that is the advantage of going for transformers. So when you say truly bidirectional, so if the use case, like you want to convert from English to French or French to English, the transformers, they have two things in them. They have encoders and decoders, two networks, okay. So what does encoders do? Encoders, they take enough English words simultaneously and creates embeddings. That's what encoders do. Take the words and create embedding simultaneously, okay. I mean, both happens parallelly. Takes the words simultaneously and creates embedding simultaneously. So what are they? They are embeddings, that is vector spaces, vectors that encapsulate the meaning of the word. So what are vectors basically? If you already known what are vectors, they are similar words. I mean, closure vectors are similar type of words. If I say is and are, might not be same words, but they are closure vectors, I can say, because they may be related to same context. If I say Prime Minister and Narendra Modi, they may be different words, but still they are connected to same. They may have near vectors because Narendra Modi is the prime minister, okay. So similar words have near vectors, okay. So that's what encoders do. They form vectors by understanding the embeddings. And secondly, the transformers have second part was decoders. So decoders, they take the embeddings from the encoders and then generate words of the translated French or Italian, whatever sentences, and it tries to predict the next word. Takes embeddings from encoders and creates the translated words, or generates the next prediction, okay. So it has separation in these tasks. Firstly, so transformers, they have two tasks, encoders and decoders. So encoders, so the main part of encoders is just not to do this embeddings. What it is doing in embeddings actually is it is trying to understand what is English, what is grammar, what is context. So it is what is happening. The understanding part is happening in encoders. In decoders, they try to map these words to the translated words. Suppose if I'm doing neural translation, so it is trying to map English to French. So encoders, what they do, they just try to understand the embedding or the language or the grammar and the context. And decoders, they just try to map the English words with French words, or they just try to do the next predictions, the mapping predictions, okay. And they both are underlying understanding of the language, okay. Both are required for a neural machine translation type of subject. you require both the understanding of the language. Even if a person, you need to understand and you need to map it. The same thing happens in transformers. So they try to understand the language and they try to map the language. Okay, so both are underlying concepts of the language. Okay, so that is what is the main functionality of transformers. Okay, which is not actually happening in any other networks. That is where the context has been recognized properly in transformers type of understanding. Okay, we haven't come to BERT yet. It is just any transformer I'm speaking about. Okay, so in this, if I say the transformers, there are two parts, right? Encoders and decoders. So encoders, I can say example is BERT. Decoders, I can something like GPT or something. Okay, maybe decoder you can say as GPT or something, but I'm example of encoder is BERT. So BERT is what? It's an encoder. So BERT is an encoder and encoder part of transformers, if I say, or anything. So BERT is an encoder. Okay, and decoder can be example of GPT something. Currently we're discussing on encoders or BERT. So here the word embeddings of BERT are little different how they are trained. Okay, so the use cases, if I say with respect to these are many neural machine translations. Let me sum them up. Neural machine translations, Q&A. I mean Q&A is what question answering system. So there's good popular use case like question answering data set. So you just ask a question to a data set, it will give the answer, like a passage comprehension, question answers. Okay, Q&A, sentiment analysis, the proper way, text summarization. See, for all these things, use cases, you understand the main part is understanding the language. That's why BERT comes into picture very good with this, because obviously any word embedding works, but BERT has more capacity because its embedding is a little more prominent in understanding the context. So for neural machine translation or Q&A or sentiment analysis, text summarization, one part is the main thing, that you need to have good understanding of context of the language. So that is very much good with BERT, and that is very much good with transformers. So that's why these use cases have better popularity than any other. Okay, so how does BERT work now? So first, there are two things on how BERT works. Firstly, the first part is pre-train, where there is called pre-training BERT to understand the language, and second thing is fine-tuning BERT to learn specific tasks. Okay, I hope this was clear. So firstly, pre-training BERT to understand language, that is embedding only in one way, and secondly, fine-tune BERT embedding, or fine-tuning BERT to learn specific task. Okay, fine-tuning BERT to learn specific task. I'll explain this. So obviously pre-training and fine-tuning. So what is pre-training? So basically the first pass, So in pre-training, it is doing embedding and trying to understand what is language, what is context, as I was saying previously. So it does pre-training, but the thing is, BERT does pre-training in two supervised tasks simultaneously. So firstly, it does pre-training in two unsupervised tasks simultaneously. Both supervised and unsupervised tasks happen simultaneously. So what are those two tasks? One is MLM. What is MLM? Mass language modeling. And secondly, NSP. Next sentence prediction. Okay, so it happens in two ways, MLM and NSP. So what is MLM? Mass language modeling. So what is mass language modeling, if I say again? So it is like fill in the blanks type of scenario. So what it does, it is trying to learn by masking some of by some of the words. Suppose if I take an example, like a quick brown fox like runs over, jumped over a lazy dog. I think the popular sentence. I'll show it. So MLM example, suppose. So if we say, so what it does is MLM. So the mask one brown fox, mask two over a lazy dog. So it is trying to predict the fill in the blanks. So the answer would be mask one is the quick brown fox jumped over a lazy dog. So it is trying to mask some of the words and trying to predict it. Okay, so goal is to output the masked words. MLM goal is to output the, okay, so that is how it's like fill in the blanks, as I said. Learning in your school, you learn things by fill in the blanks, right? Similar way, MLM is trying to learn by fill in the blanks. Okay. Secondly, NSP. So NSP is what? Next sentence prediction. So here it takes into consideration like two sentences and checks if second sentences follow the first sentence. Suppose I give an example again here. So sentence 1, Mr. Modi is great person. Mr. Modi is the PM of India, Prime Minister of India, and lives in Delhi. Okay, so these are the two sentences. It is trying to check in the next sentence prediction. It is trying to check if the second sentence follows the first sentence or not, yes or no. Okay, so it is trying to select the next sentence prediction and trying to predict kind of yes or no if second sentence follows the first sentence or not. Okay, so to summarize still here, firstly we discussed on what is the issue with LSTM, and then what are transformers, what are the advantages of transformers of LSTM, and what are transformers. They have encoders and decoders. So if I say now decoders, they create embeddings simultaneously, and decoders, they take the embeddings and do the specific next generation predictions or next predictions. And if I consider example of encoder, it's BERT, and example of decoder as GPT or something, but now we are discussing on BERT. So BERT is an encoder and it can be used in transformers as an encoder. So what are the use cases? Neural machine translation, Q&A, sentiment analysis, text summarization, where the context is very important of the language. So how does BERT work? Yeah, there are two ways. One is pre-training and there are not two ways, there are two things. First, one by one. So firstly it does pre-training, and secondly it does fine-tuning on specific tasks. So pre-training, how does it do? Again, it does on two methods. One is MLM and NSP. MLM is what? Mask language modeling. So mask language modeling. So it is like a fill in the blank scenario where it is trying to mask certain words and trying to predict it. And NSP, next sentence prediction, it is trying to check if second sentence follows the first sentence or not. So that is how till now we have discussed the summarization. So we have discussed now pre-training, and now we need to discuss on what is fine-tuning in BERT. BERT works in two ways: pre-training and fine-tuning. Pre-training is done, now fine-tuning. So fine-tuning, how does it do? It's a pass-through basically. So how to use layers in a specific context, that is important. Okay, so fine-tuning, so if I say example like Q&A, I was saying, right, the question answer scenario, so where there are a lot of question answers or paragraphs where you ask a question to BERT and give a paragraph, it will say the answer. Okay, it's like in childhood you have learned, right, the question answer of passages and comprehensions, right? So here, technically speaking, it replaces a fully connected layer of the fully connected output layer with the first set of output layers, and then the output of question answers are fed. Okay, so we already have a pre-training. So fine-tuning, how it does? It is trying to replace a fully connected layer and give the input with respect to the question answer dataset. So it is like question and passage and BERT, and it will give the answer. Like question and answer, and you give to the BERT and gives the answer. Obviously, that is a method. So things happen simultaneously. That's all. So not question answer, question and passage. Question and passage happen simultaneously, and it goes to BERT model and gives the answer. So how does it do? The fine tuning, already the fully connected layer is already there. So it is trying to replace fully connected layer. Basically connected output layer with first set of output layer and feed question answer dataset. So it's like summing up here. So it performs supervised learning with question answer dataset. That's what I can say. Okay, it performs supervised learning with question answer dataset. So previously it was still unsupervised. So it performs supervised learning with Q&A dataset or something, any dataset basically. Okay, so thing is, the advantage is it won't take too long. It won't take too long. Why it don't wait too long to train? It won't take too long to train. So it won't take too long to train because already pre-training was done, the parameters are already there, so we just need to slightly fine tune. Okay, only fine tuning is required. Already all the parameters are already trained, only we need to fine tune on the end output parameters. That's all. It won't take too long in training using BERT with any specific task, because already the parameters are trained, and we just need to slightly modify the output parameters for our specific task. So that's why I'm saying 90% job is done with BERT, only 10% has to be done. That's why it is very fast. So training time is very fast, so it can work with any NLP task. Just replace output parameters and your training dataset is done. Okay, so to go a little more in detail about the BERT understanding, I can say, let me show the BERT firstly how the BERT looks. This is the BERT attention mechanism. So this is like, I like cats more than dogs, and this is the translation Chinese, I hope so, and then Chinese. Okay, so bidirectionally it is trying to understand the encoder transformer mechanism. Okay, it is trying to get the word embeddings and then trying to work on a specific task. So if I say overview in the broad view how it is like this, just the encoders, technically speaking, just the encoders. Okay, so now the main part of BERT. So there are a lot of layers on working with BERT. So firstly, the input layer. So as you see, the structure, the architecture of BERT is like this. So it has input layer firstly. So input layer, it's simply a vector of sequence tokens along with special tokens, like written here. If you see the CLS, my dog is cute, SCP, he likes playing. Okay, so they are just simply a vector of sequence tokens with special tokens, like ing is a special token. So what is /ing? In BERT uses word piece. There's something called word piece, not world piece. Okay, so it's word piece. BERT uses word piece for tokenization, so which splits the playing as play and ing. So the advantage of using this special type of tokens is it covers it covers wide spectrum of out of vocabulary words. Okay. So here it uses word piece type of tokenization to and splits this ing and these type of words and tries to cover wide spectrum of out of vocabulary words. So it's simply a vector of sequence tokens. That's all. Input layer. Okay, and it is trying to mask, as I said, mask dog, mask likes. So it is trying to mask. And secondly, token embeddings. The second layer is so token embedding is simple. Basically, it is just the vocabulary IDs for each of the tokens. It is just trying to capture the vocabulary ID to remember in future. Use in future. Okay, and thirdly, sentence embeddings. It is just a numeric class for distinguishing between A and B. Okay, the first and second sentence. Okay, so sentence A is my dog is cute. Sentence B is he likes playing. So sentence embedding, it is just trying to it's a numeric class. It is trying to convert as a numeric class and distinguishes between the sentence A and B, and just checking whether A follows B or B follows A or not. As I said previously, what BERT does, MLM and NSP. So we only train these two in the embedding structure. So masking, that is very input layer, and token understanding, token embeddings, and sentence embeddings. Here it is just tokenizing the sentences. Okay, the numeric class. And thirdly, the transformer positional embedding, which is the important layer of BERT, which is special layer. But the main part of transformer positional embedding is token embedding and sentence embeddings are common, but transformer positional embedding is something which is part here. It indicates whether the position of each word in the sequence is right or not. So it is just trying to help you out in positioning. So whether the word is following properly or not. Next word prediction is happening based on this understanding only. Okay, to summarize this, the input layer, so it is simply a vector of sequence tokens, and it has special tokens like ing, and it uses the word piece to tokenize the BERT. And second, token embedding, so it is just capturing the vocab IDs, and sentence embedding. So it is just a numeric class for distinguishing between sentence 1, sentence B, sentence A and B. Okay, and lastly, positional embedding, transform positional embedding. So it is so simple that it tries to indicate the position of the word in the sequence. And in detail, if you see, the BERT layers are such complex. It has 12 layers, 12 layers in between. So this is structure of BERT layers, and that's how BERT works. It is so complex, but if you understand it in this methodology, it is so simple. Just two parts. One is pre-training and fine-tuning. Pre-training has MLM and NSP, masking and next sentence prediction, and fine-tuning is as per your parameters, the output parameters have to be modified for the specific task. That's all. And the advantage is it's a transformer, it is trained on a lot of data, so the embeddings will be a lot more perfect, and the context is maintained for every word. So if I say apple, it will change the context will change of the word apple. The word embedding value of the word apple will change according to sentence. See, in normal word to vec, if you heard of word to vec or glove word to vec or normal LSTM or any word embeddings, if you see the every word apple, if I say, it will have some vector assigned. It is fixed. If you say apple vector versus apple vector, it will say the distance between these two vectors is 0 because both are same. But in BERT, if I say the distance between the word apple and apple, it will be different because it depends on the context. So if I say in normal word embedding or word to vec scenario, so if there are two words, I love eating apple, or apple has released new iPhone. So in these two sentences, if you see, both have different context in this. Okay, so here apple has different understanding, here apple has different understanding. Here apple is a fruit and here apple is a company. Okay, so both are different. But if you say in word to vec, if you say the distance between apple comma apple, it will say distance is 0 of the vectors. The vector might be something like 0 1 or something like any vector. So vector might be anything, it can be some random vector. So but the distance between these two vectors is 0 because both are same. But in case of BERT, it's the same thing, but if you say the distance between apple and apple, it will have difference. If you project in a word space, okay, it will say something like 20 or 30 similarity distance or something. Okay, so thing is, the distance is varying, all the words are same, it is varying because BERT understand the context of single word with respect to multiple sentences, but word embeddings, they don't understand the context with respect to word, they understand the context with respect to same word, they understand the context with respect to different words. Suppose if I say distance between apple and orange, it will say properly, it has understood the context, apple is a fruit and orange is a fruit, so they might be near vectors. Okay, so that understanding has been done by word embedding. Okay, if I say apple and comma orange, it will say the vectors are same because both are fruits, not same, nearly same, maybe 1-2 differences because both are same type of category. But if I say apple and apple, it will not work. Okay, but in BERT, with respect to same words, it will have different understanding. So that is an advantage. Here the context is little more deeper compared to word embeddings. Okay, I hope this was clear. What is a word embedding and what is the context, and what is a word and what is its context. I hope this was clear. Yeah, I'll explain the context of this context of embedding with respect to word to vec and BERT separately now. Okay, so I just took a Colab notebook, Colab. So because this has GPU and all, it's faster speed, so it will not work in my system. So I just took Google Colab. You can use it if you want also in your systems. So I took Google Colab. So I'll explain the contextual embedding difference between word to vec and BERT embedding difference. That is the thing I want to show you now here. Word to vec versus BERT embedding difference. See, only thing that differs is context. Okay, so I have already installed Flare for now because Flare is a good NLP package and can work with multiple word embeddings. So this is quite comfortable for now for you to understand this. I'll import all the embeddings required. So one is I have imported word embeddings, which has glove, and task for embedding which has bird. Okay, in the sentence which we will work with two sentences, I will show that, and the distance between the vectors of two words, I can show that context. Okay, so now if I say I'll take glove embedding, and I'll take bird also. I think it's downloading. Glove is downloading now. So bird embedding is bird space, sorry, dash. So glove is done. Now bird, I'll be downloading the word to vector. So we have two word embedding vectors we downloaded: glove, word to vec, and bird embedding. So glove is generic, we already know, existing one. Bird is a new one, transformer embedding. So we have bird loaded and glove loaded now. So I'll have now two sentences. Sentence 1 equal to, suppose I'll take the example of Apple itself. Sentence of new iPhone 12 Pro has been released by Apple recently. And sentence 2, eating an apple is healthy, is good for health. Okay, I took two sentences. So if you see, so here the word apple has different meaning. Here the word apple has different meaning. It's here it's an no fruit. Here it's an organization. So I've just taken two sentences. So let me check the embedding of sentence 1 and sentence 2 now. I mean, we have embedded it. So sentence 1 of the word apple, -1 -2, right? It's apple there. So what is embedding now? Cent underscore 1 of -2 dot embedding. Yeah, this is my embedding for glove. And let me check the shape. The shape is 100. Okay, so it's using torch. So same thing I'll do for sentence 2 also. For token 2, suppose I'll just take for all print. Yeah, so here sentence 2, apple is this one, right? So even let me check the shape for it. So it is what? 0 1 2 3. Sentence underscore 2 of, yeah, it's apple. So let me check the embedding shape. The shape is 100. So now we have two sentences. In the sentence 1, apple is different. The sentence 2, apple is different. See, if I just so if you see here in this both sentences, the sentence 1, I'll print that also. I'm trying to explain what actually it is. Yeah, so if I see, the first sentence is eating an apple daily is good for health, and second sentence is new iPhone 12 Pro has been released by Apple recently. So if I just check these two embeddings and I only take the tensor apple token, tensor apple, so the tensor embedding for apple is same: 0.6686, 0.3490, 0.6686, 0.3490. So this glove and word embedding, what it has done, it has taken apple as one single context word and created a same vector. But if you see the sentence, here apple is not an organization and here apple is not a fruit, but the vector, the understanding as per glove is same. It has taken apple as one single word, one single context, one single vector. But actually these two should be actually different vectors, because both are in different. The spelling might be same, the word might be same, but the context is different. If I say this sentence to you, you obviously understand apple is not a fruit here. If I say this sentence to you, will obviously understand, your mind will understand automatically that apple is not a organization here, it's a fruit here, right? The same thing is not happening with this vector, with this embedding, glove embedding, right? So this is the problem in using word to vec with words like this. If I say the word different, the word embedding between apple and orange, it will say maybe, yeah, then they are nearer words, both are fruits, maybe. But if you take example of apple and apple, the distance between them is 0 because both are same vectors. Let me show that also. If we have scipy imported, so if I just say no, suppose cloud distance, so if you check the distance now, distance between these two was 0 obviously because both are same vectors. So that is the problem with using word to vec. Even though a same spelling, same word has different meanings, but the vector is same, the context is same, the distance between the two words obviously 0 because the vector is same, both are same vectors, but actually they are not same. Apple and apple are same here but not actually same. Spelling is same but the meaning is different. Okay, this issue, the contextual understanding, is solved using BERT. Contextual understanding is solved using BERT. BERT can understand what is apple in different sentences. Basically, it creates different vectors, different word embeddings for same words according to the context. This is a perfect definition of BERT. Okay, but it creates different vectors or word embeddings for same words with respect to the context. You can just write it as definition itself. It creates different vectors or word embeddings for same words with respect to context. Okay, now I'll do BERT embedding. Okay, so we already have BERT embedding. I'll just again run it for yeah, BERT is already there. So we already have sentence 1, we already have sentence 2. Yeah, sentence 1 and sentence 2 both are there. So now what I'll apply BERT embedding. Okay, and let me check the embedding now. Sentence 1 dot embedding, so it's empty. Sorry, so we can't do embedding for this, right? Sentence for a word we can do, right? Sorry, sentence word of -2. Let me check that. It's apple dot embedding. Yeah, we got a tensor like this. Let me do the same thing for sentence 2 also. And sentence 2 of 2 is what apple again, right? Now again I'll check the sentence embedding here, apple embedding basically here. Yeah, if we check this sentence 2 embedding and sentence 1 embedding, what is the difference? Both are different. -5985, -4632, 01300, and it has changed. 0.8390, 1.6440, 0.3022, -1.1050, 2021, 2334. So the embedding of apple is different here. Okay, I'll just show it clearly, the difference as before. No, I already have it here, right? Yeah, it's clear now. Sentence 1, the word is token apple and the tensor is here. Token 2 apple, the tensor is here, 2021 2334. Both are different. In the previous case, if you have seen, both are same, both are exactly same. Okay, and if suppose I check the difference, or the bird distance, suppose I write it bird distance, sentence 2 of minus 2, the embedding has changed, right? So the distance between apple and apple is 47.57, but if you check in glove, distance is 0, but the distance between here is 47. So Bert has actually understood the context here. That's why when I asked the difference between the word apple in the first sentence and the word apple in second sentence, it has understood both are not different, both are not same words, both are different words. They should have different word embedding, they should have different vectors, so both are different. So it has created two different vectors for the same single word apple and created contexts for it. So that is the advantage of using BERT. It perfectly understands the context of a single word. Okay, even the spelling is same, it can create multiple vectors, multiple embeddings for the same. That is the advantage of using BERT. Okay, if you want to just summarize, I can say the same understanding, the definition. It creates different vectors or word embeddings for same words with respect to the context. That is the advantage of using BERT over any other word embedding or any other glove. So BERT can understand multiple vectors. Thanks guys. Try to experiment with BERT. You will have a good advantage in your applications. Any use case, let me know.
Thank you for joining us on this journey through the world of neural networks. We have covered the essentials from understanding the foundational concepts to exploring advanced applications in image recognition, sequential data analysis, and natural language understanding. As you continue to explore the vast landscape of artificial intelligence, remember that neural networks are not just algorithms, they represent the future of intelligent technology. Stay curious, keep learning, and don't forget to subscribe for more insights and updates on AI. Until next time, keep innovating and harnessing the power of neural networks to shape the future. Thank you and see you soon.